Module 2, Lesson 3, Number Systems Theory. For this module, we will be discussing what is number systems theory, especially the divisibility theory, the integer representations that are used for your computer, decimal to base n conversion, and base n to decimal conversion, and finally, different binary code representations that are used by your computer. What is number theory? Number theory is the part of mathematics devoted to the study of the integers and their properties. Number theory has long been studied because of the beauty of its ideas, its accessibilities, and its wealth of open questions. The key ideas in number theory include divisibility and primality of integers. Representations of integers, including binary, hexadecimal representations, are part of number theory. The divisibility theory. According to the definition, if a and b are integers with a not equal to 0, then a divides b if there exists an integer c such that b is equal to a times c. When a divides b, we say that a is a factor or divisor of b and that b is a multiple of a. The notation is often used for the principle that a divides b. If a divides b, then b over a is also an integer. If a does not divide b, then the common notation is given in this particular form. The division algorithm. When an integer is divided by a positive integer, there is a quotient and a remainder. This is traditionally called the division algorithm, but it's really a theorem. According to the division algorithm, if a is an integer and d a positive integer, then there are unique integers q and r with r between 0 to d such that your corresponding integer a is equal to d times q plus r, wherein d is your divisor, your a is your dividend, your q is your quotient, and your r is your remainder. There are different definitions then of your division function and your modular division function as expressed in the given textbook. Your q is equivalent to a div d, or a divided by d, while your r is equivalent to a modular division, or mod d. This is one such example. What are the quotient and remainder when 101 is divided by 11? The solution is, when 101 is divided by 11, is 9. Therefore, 9 is equal to 101 divided by 11. And the remainder is 2, therefore 2 is equal to 101 mod 11. There are different integer representations in algorithms. In the modern world, we often use decimal or base 10 notation to represent integers. This is one such example whereby we try to evaluate 965, whereby 9 is multiplied by 10 raised to 2, plus 6 multiplied by 10 raised to 1, plus 5 multiplied by 10 raised to 0. So all these particular values are multiplied by a base of 10. We can represent integers using any base where b, or base b, is a positive integer that is usually greater than 1. The common bases that are often seen on computers and communication are base 2, which is a binary, base 8, which is octal, and base 16, which is a hexadecimal. The ancient Mayans actually used base 20, and the ancient Babylonians actually used the base 60. These are the different numbers with their corresponding different bases. Therefore, these particular values would be equivalent to that same particular amount, but on a different particular base value. Hence, your corresponding 0 is often the first value seen on any particular base number. Okay? And when you have base 10, It means that there are 10 unique characters that are essentially seen on your corresponding decimal number, which provides unique values on your particular decimal number. They are the values 0 all the way to 9. These are the unique values of your base 10. Hence, there are 10 values of this given particular value included in your base 10. Note that your corresponding base 10 actually does not count only up to 9. You could actually count beyond 9. As you observe, the sequence is simply repeated, but the value on the next higher place value of 10 starts off with the next corresponding digit found in your decimal. This is the pattern that is very evident on any particular number system. As you've seen, on a base 2, there are only two particular values that represent value in your binary number. They are 0 and 1. Therefore, in order to come up with different combinations of zeros and 1, you'd end up with more corresponding bits that represent your corresponding value. And accordingly, on our base 2, this particular value now represents a value of 1. This represents a binary value of 2, 3, and so on and so forth. However, on an octal value this time, your respective 1 is still equivalent to a value of 1. Since there are 8 unique characters that are used for your base 8, starting from 0 all the way to 7. So notice that from 0 to 7, the value is similar to your decimal number. However, the system repeats the sequence of 0 to 7. However, the next higher place value is preceded by the next number in the sequence, which is 1. Therefore, this particular value then represents a value of 8 in your octal. Whereas on a hexadecimal, you will notice that it has 16 unique characters that represents value in your hexadecimal, starting from 0 all the way to 9, and then A all the way to F, representing values 10 to 15. How do we then determine these different base B notations? We can actually represent any particular integer b that is greater than 1 using this particular theorem. If we let b be a positive integer greater than 1 and n a positive integer, it can be expressed uniquely on this given particular form. Which means if your k is a non-negative integer, therefore a subscript 0 all the way to a subscript k are non-negative integers that are less than b. And your a subscript k should not be equivalent to 0. Therefore, your a subscript j, where j is equal from 0 to k, are called base b digits. And these particular digits are representations of your radix or your base power. The representation of n in theorem 1 is called the base b or the base r expansion of n, and is denoted by a subscript k all the way to a subscript b. However, we usually denote and omit the subscript for a base 10. So meaning for any base 10 expansion, we often do not place the base 10 because by default, we often describe values always in base 10. Hence, a quantity like 7,392 is basically broken down to 7 multiplied by thousands, therefore you end up with 7,000, 3 multiplied by hundreds, therefore you end up with 300, plus 9 multiplied by tens, therefore you end up with 90, plus 2 multiplied by 1, therefore you end up with 2. And it's written as the same concept is then applied for any base n notation in order to determine its value in decimal number. There are many different number systems. However, in general, we often express base R system as coefficients that are multiplied by the powers of R. The coefficients A subscript j range from values from R to 0 up to R minus 1. Therefore, if you have like a base 10, you only have from 0 to 9. If you have a base 2, you only have from 0 to 1. If you have a base 8, you only have values from 0 to 7. And if you have a base 16, you only have values 0 to 15. So if you have a particular number called base 5, you only have values from 0 to 4. Therefore, 4021 base 5 simply means 4 times 5 raised to 3 plus 0 multiplied by 5 raised to 2 plus 2 multiplied by 5 raised to 1 plus 1 multiplied by 5 raised to 0, giving you a value of 511 in base 10. Hence, this particular theorem converts any particular base number into a base 10 or our decimal notation. The binary number system, which is a base 2. The binary number system is different since the particular values are only represented by two possible values, which are 0 and 1. Hence, the radix is simply a power of 2 or a base 2. The radix, which is the value of power under base 2, is often used, and the results are added to obtain the decimal equivalent of your corresponding number. The radix point, or similar to your decimal point, eventually distinguishes the power of your corresponding base from positive to negative. For example, let's determine the equivalent value of the binary number 11011 base 2. If we eventually evaluate its decimal equivalent value, you would have 1 multiplied by 2 raised to 4 plus 1 multiplied by 2 raised to 3 plus 0 multiplied by 2 raised to 2 plus 1 multiplied by 2 raised to 1 plus 1 multiplied by 2 raised to 0, giving us a value equivalent to 27 base 10. This is another example of your binary number. If you're given 10101111 base 2, therefore you end up with this corresponding solution, ending up with a decimal value of 351. As noted, the digits of your binary numbers are called bits. When a bit is equal to 0, it does not contribute to any sum during the conversion. Therefore, the conversion of binary to decimal can be obtained by adding only the numbers with powers of 2 corresponding to bits that are equal to 1. There are 4 ones in a binary number. The corresponding decimal number with the sum of 4 ones is equivalent to a power of a decimal value of 16. 0 and the first 24 numbers obtained from 2 to the power of n are listed on the next table, which eventually shows you the given power of 2 and often the associated corresponding table given here showing you powers of 2 and the common notation that are often associated with powers of 2. The octal number system or base 8. The octal number system or base 8 corresponds to have 8 unique characters starting from 0 all the way to 7. It is customary to borrow the needed R digits for the coefficients of your decimal system when the base of the number is less than 10. Note that the digits 8 and 9 cannot appear in your octal number system. So hence, if you're given an octal number of 111 base 8, therefore the equivalent decimal value of this would be 1 times 8 raised to 2 plus 1 times 8 raised to 1 plus 1 times 8 raised to 0, which gives us a total summation of 73. And the hexadecimal number system or a base 16. The letters of the alphabet are used to supplement the 10 decimal digits that are used for your hexadecimal number systems for values that are greater than 10. In the hexadecimal number system, which is a base 16, the first 10 bits are borrowed from your decimal system, followed by the letters A, B, C, D, E, and F, used to represent the values 10, 11, 12, 13, 14, and 15, respectively. The hexadecimal system is actually used commonly by designers to represent very long strings of bits and addresses and instructions and data in digital systems. Here's one example when converting your corresponding hexadecimal number to a decimal number. Let's say you have E5, which is base 16. Therefore, E represents a value 14 times 16 raised to 1 plus 5 multiplied by 16 raised to 0. Therefore, you end up with a value of 229. Another example would be the hexadecimal number 2AE0B. Your 2 represents there and is multiplied by 16 raised to 4 plus 10 raised to 16 raised to 3 plus 14 times 16 raised to 2 plus 0 times 16 raised to 1 plus 11 times 16 raised to 0, giving you a corresponding decimal value of 175,627. Number conversions. Representations of numbers in different radix are said to be equivalent if they have the same decimal representation. For example, 0011, which is basically 8, and 1001, which is 2, are eventually equivalent and both have a decimal value of 9. However, one is a base 8 while the other one is a base 2. The conversion of a number base r to decimal is done by expanding the number in a power series based on the theorem and adding all the terms as shown previously using theorem 1. The general procedure for the reverse operation of converting a decimal number to a number in a base r is basically done by using the division theory. If the number includes the radix point, it's necessary to separate the number into an integer part and a fractional part, since each part must be converted differently. The conversion of a decimal number to a number in base r is done by simply dividing the number and all successive quotients by r and accumulating the remainders. To construct base b expansion of your integer n, you end up with the following steps. Divide n by b first to obtain a quotient and the remainder. So n is equal to b times q0, which is your quotient, plus a0. Remember, your a0 or corresponding remainder is always between 0 and your base b. Next, the remainder a0, which is the rightmost digit in your corresponding base b expansion of n, and then next divide q0 by b again. Therefore, you end up with another corresponding quotient, which is b times q1 plus a1. a1 again is a remainder that is between 0 to your corresponding base b. The remainder a1 is the second digit from the right in the expansion of your corresponding base b number. Continued on successively dividing it until the corresponding respective remainder value becomes less than 1. The process eventually terminates when the quotient is 0. The conversion of the decimal integers to base b radix system is similarly applied to any particular base r. For example, let's convert 41 to binary. In converting 41 to binary, we divide 41 by 2, therefore we end up with a remainder of 1. And then we continue dividing 20, which is the quotient, by 2, so we end up with 10 with a remainder of 0. And then we continue to divide 10 with 2, you have a value of quotient of 5 with a remainder of 0. And then if we divide 5, we end up with 2 with a remainder of 1. And then when we divide 2, you end up with a quotient of 1 with a remainder 0. And finally, if we divide the quotient 1 by 2, we end up with a value less than 1. Therefore, we end up with 0 plus your corresponding remainder 1. Therefore, your corresponding 41 base 10 is equivalent to 101001. Notice that the corresponding coefficient of your respective remainders is often read from the bottom up when evaluating your corresponding respective base n equivalent of your decimal number. This is particularly commonly done when you often convert any number to any base n. Basically, this is how your corresponding arithmetic operation for your respective conversion from a decimal number to a binary number as shown. Let's try to convert a decimal of 153 to octal. The same process is done, but this time we divide everything by 8. Hence, we end up with the following remainders. When read backwards, you end up with a corresponding octal equivalent value of 231 base 8, equivalent to your decimal 153. The conversion of a decimal fraction to binary is accomplished by a similar method. However, instead of dividing it, you multiply your corresponding fractional part by your base r. The multiplication process is continued until the corresponding fractional part becomes 0, or until the digits have sufficient accuracy value. Let's try to convert 0.066875 base 10 to binary. When we do that, we simply multiply 0.6875 by 2. You end up with 1.375. You get the whole integer 1, and then the remaining fraction 0.375 is multiplied by 2 again. And if you multiply that by 2, you end up with the corresponding product of 0.75. Therefore, your whole integer value there is 0 with a fractional part of 0.75. You multiply 0.75 by 2, you end up with 1.5. You get the integer part, which is 1, and multiply the remaining fractional part 0.5 by 2 again, until you end with an integer value of 1 with a fractional part of 0. Therefore, you then read the corresponding fractional part of your respective binary number, this time from top to bottom. This now would be the equivalent decimal value of 0.6875 base 10 to your base 2, which is equivalent to 0.1011 base 2. Let's convert 0.513 base 10 to octal, and eventually it will then be as follows. You will notice that when multiplying it by 8, you end up with a fractional part every time. Therefore, this particular decimal value 0.513 would end up with a non-terminating base 8 decimal equivalent, which is basically equivalent to 0.406517, and so on and so forth. Now, depending on how many decimal numbers, digits that are included on your base 8 that you require for accuracy. The conversion of binary, octal, and hexadecimal numbers. Basically, the conversion from binary to octal and hexadecimal plays an important role in digital computers because shorter patterns of hex characters are easier to recognize than long patterns of ones and zeros. Let's say we want to convert binary to octal. To convert binary to octal, this is easily accomplished by partitioning the binary number into groups of 3 bits, starting from the binary point, proceeding to the left and to the right, adding zeros as needed. So let's say we want to find the octal equivalent of this corresponding binary number. So simply group them into 3, starting from the least significant bit, and then simply append a 0 on the most significant bit, and then replacing each corresponding group of 3 bits by your corresponding octal equivalent number. As shown here, this is equivalent to an octal value of 4, this one 7, this one 2, this one 7, and this one 3. Likewise, this example. When converting binary to hexadecimal this time, you simply divide your corresponding binary numbers into groups of 4. Like, for example, I wanted to find the hexadecimal equivalent of this binary number. Therefore, we simply group them into 4s, again appending values on the most significant bit, starting from the least significant bit. And accordingly, on each group of 4, we simply convert each group of 4 into a character in your hexadecimal. This is equivalent to the character C, this one B, this one E, and finally this one into a character of 3. Therefore, the hexadecimal equivalent of this particular binary number is 3EBC base 16. This is another particular example that contains your corresponding decimal value. Conversion of octal to hexadecimal to binary. When converting octal to hexadecimal, it is often applied that it goes through binary value first. So when you convert, for example, a base 8, you simply convert that first, each character of base 8 into a binary number, and then join them together, and then afterwards group them into 4s. Therefore, you end up with this corresponding equivalent of your octal 673.124 base 8 into 306.B base 16. The different signed binary numbers are seen here, and as you could see, negative numbers are also represented in your corresponding binary number. There are different binary coded decimals that are often applied for your computer, one of which is called the binary coded decimal, whereby this corresponding digit represents only values 0 to 9. However, your BCD digit is always fixed to 4 bits, and there are corresponding representations that are not used in your decimal value. Likewise, there are other weighted codes that are often applied for your decimal digit, such as your 2421, your excess of 3, and your 84 -1 -2. You also have the gray code. The gray code is often used to represent sequences whereby binary numbers change only a difference of 1 bit. You could also represent the corresponding letters or any of the operations in your computer using binary numbers based from the American Standard Code for Information Interchange. Arithmetic operations with numbers in base R eventually follows the same rules for your decimal numbers. When a base other than your familiar base 10 is used, one must be careful when allowing or evaluating corresponding arithmetic operations. So arithmetic operations involving your binary numbers is often referred to as the Boolean algebra. These particular operators are defined by the Boolean sum, which is a 1-bit addition, having this corresponding rule, the Boolean product, which is a 1-bit multiplication, having this corresponding values, the complement. For example, let us find the value of this corresponding Boolean algebra. Therefore, in order to solve for that, we evaluate first operations inside your brace, which is 0 plus 1, we end up with a value of 1. And then we complement 1, therefore we end up with 0. And then 0 plus 0, therefore we end up with a value of 0. Examples of different addition, subtraction, and multiplications of two binary numbers would be as follows and as seen on this given example. And they are performed in the same way similar to your decimal numbers. This ends our corresponding module. For this corresponding lesson, we have covered the different operations involving your binary numbers and logic bit operations.